Okay, so this is lesson 11 on the chain rule. And this is the last section before the first exam. So our schedule is on Monday, which is the 18th. We review for exam 1. And on Wednesday, which is the 20th, we take exam 1. So we had no class on Monday because of school was closed. Last week we did the last thing, the product and the quotient rules. Are there any questions about either one of those? So maybe as a kind of warm-up, I'll do a few exercises from the homework involving the product rule and the quotient rule. So this was section 3.3. Number 45. We have the function g of t, which is written like this: the fourth root of t plus 6 times the cosecant of t. And it's a little bit easier if you write roots as exponents. So the fourth root of t is t to the power 1/4, and the cosecant is 1 over the sine. So to differentiate this function, to differentiate t to the 1/4, that's just the power rule, 1/4 t to the 1/4 minus 1 plus 6. The derivative of 1 over the sine, if we use the quotient rule, it's sine squared t in the denominator. This is like, well, I'll just write it as sine squared in the denominator. The derivative of the numerator, which is 6, is 0 times the denominator, minus 6 times the derivative of the denominator, which is cosine t. So this is t to the minus 3/4, so that's 1 over 4 t to the minus 3/4 minus 6 cosine t over sine squared t. Sometimes people like to write that as minus 6 cosine t over sine t times 1 over sine t, in which case this is 1/4 t to the minus 3/4 minus 6 times the cotangent of t times the cosecant of t. And that's what it is. And then we do number 69. In number 69, we have the function f of x equals x minus 1 e to the x. And we want to find the tangent line to the curve going through the point 1, 0. Okay. When you let x equal 1, f of 1 is 0. So the tangent line has a slope, which is the derivative. So we need to find the derivative of this function. We use the product rule. The derivative of x minus 1 is 1 times e to the x plus x minus 1 times the derivative of e to the x, which is e to the x. So this is equal to e to the x plus x e to the x minus e to the x. So we're left with just x e to the x. And if we evaluate this at 1, we get 1 times e to the 1, which is e. So what is the tangent line? It's y is equal to the derivative of 1, which is e, times x minus 1, plus the value of the function at 1, which is 0. So it's simply this. It's ex minus e. So this is the line with y-intercept minus e and going up with slope e. That's the tangent line. Any questions about this? Also assigned from section 3.2 were problems 105, 107, and 111. Let's do some of those. So this is section 3.2, number 111. So you have a cube with side S. So this is a cube. And the volume of a cube of side S is S cubed. Now, so the volume is a function of S. Find the rate of change of the volume with respect to S when S is 6 centimeters. So dV ds is just 3s squared. So at s equal to 6, dV ds is 3 times 6 squared, or 3 times 36, or 108. That's the rate of change of the volume with respect to the side S. Let's look at number 107. So number 7, we have a velocity function. And as a function, so here we have the time, and here we have velocity. So this is the time measured in minutes, and the velocity measured in miles per hour. And from 0 to 6, and 20, 30. For the first 6 minutes, the car is moving at 40 miles an hour. For the next 2 minutes, its velocity is 0, from 6 to 8 minutes after the start. And for the last 2 minutes, it's going at 60 miles an hour. So you're looking at your speedometer. It's a 10-minute drive. You drive, for the first 6 minutes, you're driving 40 miles an hour. Then you're stopped for 2 minutes. And then for the next 2 minutes, you drive at 60 miles an hour. Make a sketch of the corresponding position function. So this is velocity. And what is position? So this is position. This is time. And here you're going to be measuring position. So if you think about this, you're driving 40 miles an hour for the first 6 minutes. So 40 miles per hour, that's 40 miles for every hour. How fast is that per minute? Well, it's 40 miles per hour, but 1 hour is 60 minutes. So this is 40 over 60, or 2/3 miles per minute. So traveling 40 miles an hour is the same as driving 2/3 of a mile every minute. So for the first 6 minutes, each minute you're traveling 2/3 of a mile. So every 2 minutes, you're traveling 4/3 of a mile. 4, 8/3. After 6 minutes, you've traveled 4 hours, 4 miles. So for the first 6 minutes, you're traveling 2/3 of a mile per hour. At the end of 6 minutes, you're moving at a constant velocity. At the end of 6 minutes, you've traveled 4 miles. But for the next 2 minutes, you're not moving at all. Your position doesn't change. So you're horizontal from 6 to 8. And then for the last 2 minutes, you're driving at 60 miles per hour, which is 60 miles per hour, 1 hour for every 60 minutes. That's 1 hour per minute. So now you're going up faster. In 2 minutes, you go 2 miles. So this is 10:6. That's the coordinates of this point. This is 8:4. This is 6:4. So this is your position as a function of time. Goes up at a constant rate, 2/3, horizontal, 0 slope, 0 velocity, and then goes up faster, slope 1. All right. And then let me just do one more because these are kind of fun. This is number 105. Here we had the velocity as a function of time and we wanted to find the position. In 105, we're given the position as a function of time and we want to find the velocity. So in 105, the position is the following. Over 10 minutes, and the distance traveled, let's see. So for the first 4 minutes, the position is increasing at this constant rate till you get to, after 4 minutes, you've traveled 2 miles. Then for the next 2 minutes, your distance doesn't change. So from minute 4 to minute 6, you're still 2 miles from where you start. And then for the last 4 minutes, your distance is increasing from being 2 miles away to being 6 miles away. So what does this say about your velocity? So in 4 minutes, you go 2 miles. So you're going half a mile a minute. So from 0 to 4, you have constant velocity a half, 1/2 mile per minute. Right? This line has slope a half. This is velocity. I'm doing this in miles per minute. From minute 4 to minute 6, your distance doesn't change. You're not moving. Your velocity is 0. And then for the last 4 minutes, you move 4 miles. So from minute 6 to minute 10, you go from 2 miles away to 6 miles away. 4 miles in 4 minutes, you're going up with slope 1. So you have your velocity is 1. From minute 6 to minute 8. So for the first 4 minutes, you have constant velocity, 1/2 miles per minute. Then you don't move, your velocity is 0. Then your velocity is 1 from minute 6 to minute 8, 1 mile per minute. So that's actually very nice. That is, it's important to understand what calculus means. Okay. So if you've seen the lecture, as I hope you have, lecture 11, that describes the chain rule, which is the most useful rule in mathematics, everything, in calculus, certainly, for differentiation. And the chain rule has to do with a composite function. So the chain rule tells you how to differentiate, that is, find the derivative, a composite function. So the idea always is, when you have a function, you have some function g, which takes x to some number g of x. So let's say u is this function g of x. But then for every number here, you have a function f, which sends g of x to f of g of x. So this gives you, this is some number u, and y is f of g of x. So y is some function of u. And when you put the two of them together, this is the composite. Y is equal to f of g of x, which we write as f composed with g of x. It's not product, it's composition of functions. And the chain rule tells us the following. The idea is f might be a simple function and you know its derivative. G might be a simple function and you know its derivative. When you put them together, you might get a complicated function. But the chain rule tells us how to find the derivative of that complicated function in terms of the simpler functions. So we have y is some function of u, f of u. U is some function g of x. So we have the composite, y is f of g of x. And dy dx, this is the derivative. This is, the shorthand is dy du dx. dy du means f prime evaluated at u. Du dx is g prime of x. So this is the chain rule. The derivative of f of g of x, it's f prime evaluated at g of x times g prime of x. So let me do a number of examples of using the chain rule to differentiate a function. So again, this is the chain rule. The derivative with respect to x of f of g of x is f prime evaluated at g of x times g prime of x. So here are some examples. Some of these can be done differently, but and I'll follow the nice table that is in the book. I mean, partly the idea is you have to know how to disentangle a function. So suppose you have the function y equals sine of 2x. You can think of this as a composite. You can have y is equal to the function f of u, which is the sine of u, and g, which is some, and u is some function f g of x, which is 2x. So if you compose these two, f of u is sine of u, g of x is 2x. So when you put them together, f of g of x is the sine of 2x. Suppose we have y equals the square root 3x squared minus x plus 1. You can think of y as some function f of u, which is just the square root of u, and u is some function of x, which is 3x squared minus x plus 1. So this is easy to differentiate. This is easy to differentiate. This looks complicated. But see, when you disentangle it in this way, we have y is f of g of x. That's the square root of g of x. That's the square root 3x squared minus x plus 1. Now, in this example, let's find the derivative. G of x is 3x squared minus x plus 1. So g prime of x is derivative of this polynomial, 6x minus 1. F of u is the square root of u, which is u to the 1/2. So f prime of u is 1/2 u to the minus 1/2, or 1/2 times the square root of u. So what is dy dx? It's f prime of g of x, g prime of x. F prime of u is 1/2 times the square root of u, and u is 3x squared minus x plus 1. And g prime of x is 6x minus 1. So we get 6x minus 1 over 2 times the square root of 3x squared minus x plus 1. Okay, that's the derivative. Any questions about this? This is really a fundamental differentiation rule. And you'll see as you go through the semester and next, you use the chain rule all the time. Suppose y is x squared plus 1 cubed, and you want to find dy dx. So you can think of this as a composite function. If you had, this is f of g of x, where g of x would be x squared plus 1, and f of u would be u cubed. Because when you compose f of g of x, that's x squared plus 1 cubed. G prime of x is 2x, and f prime of u is 3u squared. So dy dx by the chain rule, this is f prime of g of x, g prime of x. F prime of u is 3u squared. So if u is g of x, that's 3 x squared plus 1. That's my u. That's g of x squared. G prime of x times 2x. So this is 6x times x squared plus 1 squared. Any questions about this? So you can generalize this and get what is called the general power rule. It says that if y is some function u of x raised to the power n, dy dx is n u of x to the power n minus 1 times u prime of x. This is exactly the chain rule. If you let f of x be, f of u be u to the n, you would get n u to the n minus 1 times u prime of x. So for example, if f of x is 3x minus 2x squared cubed, this is like u of x cubed, where u of x is 3x minus 2x squared. So this is my y. Dy dx, or f prime of x, is n is equal to 3 u of x to the n minus 1. 3 minus 1 is 2. U prime of x, the derivative of u, is 3 minus 4x. And the powers, of course, don't have to be positive integers. They can be fractions, they can be negative, whatever they might be. So for example, suppose f of x is the cube root of x squared minus 1 squared. So a cube root is raising whatever is inside to the 1/3 power. So this x squared minus 1 squared to the power 1/3, which is the same as x squared minus 1. 2 times a third is to the power 2/3. So this is like u of x to the 2/3, where u of x is x squared minus 1. So f prime of x, my exponent is 2/3. 2/3 u of x to the 2/3 minus 1 times u prime of x, which is 2x. 2 times 2 is 4x over 3. This is to the minus 1/3 over the cube root of x squared minus 1. Right. Any questions about this?
Professor,
Yeah.
I have a question about the exam. So is the exam considered a midterm or no? Or just an exam?
Oh, it's a midterm. I mean, it's the same thing.
Okay,
I mean, there are 2 exams before the final. So you can call them
Okay.
midterms or not, but I mean, I call them exam 1 and exam 2. You want to say it's midterm 1 and then midterm 2, that's okay also.
Okay. Thank you.
Sure. Well, let's do some more. Because the chain rule is something that you have to learn to do efficiently. Suppose we have the function g of t is minus 7 over 2t minus 3 squared. So you could use the quotient rule, but then the quotient is this, which is a composite function. It's actually a little bit easier to write this as minus 7. And 1 over 2t minus 3 squared is 2t minus 3 to the power minus 2. So we can think of this as minus 7 u of t to the power minus 2, where u of t is 2t minus 3. That's what we're putting in there. So g prime of t is minus 7. And then you get minus 2 u of t to the minus 3 times u prime of t. So minus times minus is plus. This is 14. U of t to the minus 3 is 2t minus 3 cubed in the denominator. And u prime of t is just 2 times 2. So this is simply 2 times 14, 28 over 2t minus 3 cubed. Let's look at one more example. Suppose f of x is x squared times the square root of 1 minus x squared. So this is a product times something that's a composite function, x squared times 1 minus x squared to the half. So let's first use the product rule. F prime of x is the derivative of x squared, which is 2x, times 1 minus x squared to the 1/2, plus x squared times the derivative of 1 minus x squared to the 1/2. And for this, so here I just use the product rule. But to differentiate this, I need the chain rule. This is 2x times 1 minus x squared to the 1/2 plus x squared. I get 1/2 times 1 minus x squared to the minus 1/2 times the derivative of 1 minus x squared, which is minus 2x. So this is 2x times the square root of 1 minus x squared. The 2's cancel. I have a minus sign, and I have x squared times x. So minus x cubed, 1 minus x squared to the minus 1/2 over the square root of 1 minus x squared. And if I put this over a common denominator of the square root of 1 minus x squared, I have to multiply this top and bottom by the square root of 1 minus x squared. I get 2x times 1 minus x squared minus x cubed. This is 2x minus 2x cubed minus x cubed minus 3x cubed over the square root of 1 minus x squared. Or if I want, I can factor an x out of this, x times 2 minus 3x squared over the square root of 1 minus x squared. Now, one of the fundamental functions that we have not learned yet how to differentiate is the logarithm, which always means the logarithm to base e. So we want to figure out, how do you differentiate natural log of x? So what we can say is if y is equal to the log of x, that means that x is equal to e to the y. And now we can use the chain rule. The derivative of x with respect to x, of course, that's 1. But that's the same as the derivative of e to the y with respect to x, where y is log x. This is the derivative of e to the y with respect to y times dy dx. The derivative of e to the y is e to the y. So what we get is that dy dx equals 1 over e to the y. What is e to the y? Y is log x, e to the y is x. This is 1 over x. Y is log x, the derivative is 1 over x. So this is a very slick proof of the following fundamental differentiation formula. The derivative of log x is 1 over x. And I'll give that guy a star because it really is important. So suppose, for example, we wanted to find the derivative of the log of x squared. Of course, we could use the chain rule. This would be the derivative of the log of u, where u is equal to x squared. So this would be the derivative with respect to u of log of u times du dx. The derivative of log u is 1 over u, and the derivative of u with respect to x is 2x. So this is 2x over x squared, which is 2 over x. That's using the chain rule to find the derivative of the log of x squared. Of course, there's a much easier way, because the log of x squared is just 2 log x. You can always take, when you have the log of x to a power, you can always move the power in front. So the derivative with respect to x of the log of x squared is just 2 times the derivative of the log, 2 over x. So of course, we get the same result, but this method in this case is a little bit easier. Suppose we want to find the derivative of the log of the sine of x. This is a composite function. This is like the derivative with respect to x of the log of u, where u is sine x. So this is the derivative of log u with respect to u, du dx. Derivative of log u with respect to u is 1 over u. U is sine x, the derivative of the sine is the cosine. So we get 1 over u, that's 1 over the sine, times the cosine. That's exactly the cotangent. So we have this nice formula, the derivative of the log of the sine of x is the cotangent of x. So this is the last differentiation formula. We now have all the rules we need to differentiate any function we come across, no matter how complicated it looks, because complicated functions almost always are composite functions of one sort or another. Let me do one or two more, and then if there are no questions, we'll stop for the morning. So suppose we have the function f of x equals the log of x times x squared plus 1 squared over the square root 2x cubed minus 1. So that truly looks like a mess, but we can simplify it by using properties of the log. Remember, the log of AB is log A plus log B, and the log of A over B is log A minus log B. Right? So these are basic properties of the log. And here, first of all, I have a quotient. So this is the log of x times x squared plus 1 squared minus the log of the square root of 2x cubed minus 1. Of course, this is the log of a product. So this is log x plus times the log of x squared plus 1 squared minus the log square root is the same as power 1/2. And we know the log of a to the k is k log a. So I can take these powers outside. This is log x plus 2 times the log of x squared plus 1 minus 1/2 times the log of 2x cubed minus 1. So now I can differentiate using the chain rule, f prime of x. The derivative, I differentiate term by term. The derivative of log x is 1 over x. The derivative of, so this is plus 2. This is a composite function. The derivative of the log of x squared plus 1 is 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x, minus 1/2. The derivative of this log is 1 over 2x cubed minus 1 times the derivative of 2x cubed minus 1, which is 3x squared. Oops, sorry. 2x cubed, and I differentiate that, I get 6x squared. So that's the result. Now, I cannot overemphasize how important it is to learn the chain rule. And the more problems you do, the better, because almost every differentiation problem you come across in calculus from now on will involve the chain rule. Okay, I don't want to get ahead, certainly, and I will set up an office hour or two later in the week, so If you're doing problems and you have some questions, I would encourage you to log into one of the Zoom office hours. And happy to help you with anything that's giving you a problem. Any questions about any of this? Anything we've done so far? This is as far as the first midterm goes. It's basically differentiation and technique, basically techniques of differentiation, learning how to differentiate functions. And a large part of the test will just be a list of functions and we say differentiate them. That's what it is. And the best way to prepare is to review homeworks. And Monday's class will just be a review class. I'll just be here to answer questions. And as long as you have questions, I'll be here to answer them. Any questions? If not, then that's it for the problem session. Have a good weekend, everyone.